Hi, I'm Oliver from Origami Digital, and welcome to an introduction to VDBs in LightWave 2019. This video is not an in-depth guide to VDB, but more of a getting started in the wonderful world of VDBs and what's possible in LightWave 2019. What are VDBs? You can essentially look that up on the VDB webpage, openvdb.org. And if we just take a look at them, you can see that some of them are looking like solids and other ones look like smoke. These solids are essentially called level sets, whereas the smoke or fire or gaseous VDBs would be more called fog volumes. In previous versions of LightWave 2019, you can actually load the fog volumes, but you couldn't create them. You would have to use a second application. As of LightWave 2019, you can now not only create fog volumes, but also level sets right inside LightWave. First, we're going to look at the concepts of VDB creation. And since level sets are new, we're going to look at those first. Whether you work with level sets or fog volumes, they can be created from objects, particles, or primitives. We're going to start by just making a couple objects. We're going to make a toroid, and we're going to make a sphere. And then we're going to position the sphere a little bit, something like that. Now we're going to hide them or make them a bounding box so that we can still know where they are. And in order to create a level set in LightWave 2019, you have to add a null object. And under object replacement for that null, you will find an OpenVDB evaluator, and that's essentially where your level sets are. Click Properties, and we get a node editor. Under the node tree here, you can see that there's a new subcategory called OpenVDB, and all the tools that you need for VDB access are basically compiled in here. Since we know that these were objects, we're going to add two mesh to volumes, and that's essentially one for the toroid and one for the sphere. Inside of here, we have a couple options. We need to pick the mesh that we wanted to have, use. So target mesh will start with a toroid. We wanted to create a level set and not a fog volume, and we want to use world space so that if we move the objects in here, that the transformation gets automatically passed on, and it's not just in local space. We're going to do the same for the sphere, level set, and also world here. And notice how we have a world or a voxel size here of 5 centimeters, essentially. That this value is in meters. And what we want to do here so that we don't have to change them every single time in every node, we're going to add a scalar here. Scalar. Where is it? We're going to add a scalar here. At 0.05, and now we can control it with one value. So if we just plug the output here, you can see there's a grid output and there's a grid input here. If we plug the output of 1, you can see that this would be the VDB meshed version of the original toroid, and this would be the sphere. In order to combine them, we can use a Boolean operation, and you can find that under CSG. And you can see CSG has multiple inputs. In this particular case, we only have 2. So any CSG operation of the same type, you can just add as many as you want. So here we're going to add our toroid as 1 and the sphere as second one. And we're going to plug the output into the input here. And you can now see that this is essentially already meshed. You can see that there's a little bit of an overlap here, and that's the nice thing about VDB. It's essentially a single object that's been meshed together. We have different modes under the Booleans. We have union, which essentially adds both of them together. Intersection just takes the intersecting space. And then we can also subtract the sphere from the mesh. The nice thing is that everything is essentially procedural. So we can take our sphere and we can move it around. And you can see as we move it around, it's a live representation of what you're doing. Going further, you can see that this is a little bit coarse and maybe not exactly to the size of the sphere that you initially had, but that's because of our resolution here. If we change the resolution to 0.01, for example, you can see that once we update the timeline, you can see that that's now a lot more precise. Of course, that's going to get slower, not much, but for the purpose of this tutorial, 0.05 will perfectly be beneficial and fine. We also have filters, which is the next node here. Filters, if we hook it up, not a lot of happens by default, but we have a lot of different filter modes, and the 3 most common are going to be dilate, which essentially allows you to grow the object outwards, by the voxel offset, which is essentially the size of a voxel. So if we do 3 here, you can see it grows nicely. If we choose erode, it will make it smaller to what it initially is. If we do it to 0, it'll go back to the original. So you can kind of see, we're changing, making it smaller. And then you also have a Gaussian filter, which essentially smooths everything. So you can see it's much smoother now than what we had before. On top of that, you can then, of course, later on add a noise. That's another thing to nicely break up your surface at times. Before we do that, we're going to add a new procedural node, which is a nice node that encompasses all your procedurals in one node. We're going to keep the turbulence here, make the foreground color white, go to options, make this 100% so that we can kind of see a little bit of something. Plug the value into the input of the noise, plug the grid into noise and the output right here, and you can see now that we've added some noise to it. And you can layer these things as much as you want, smooth again, dilate, all kinds of different things to make these things come together. And that's essentially the most simplistic way of adding objects together. You can, of course, do all of this and then add a second Boolean or more meshes together at your heart's content. Now let's do something a little bit different and actually delete the sphere. So we're going to remove the sphere, remove it from here, don't need that anymore. We won't actually need the Boolean, so we're just going to be left with our toroid here that's being meshed. Now you can also put particles on this surface. These are just regular objects, but VDBs also have a particle section. So we can go again to the OpenVDB nodes. And there's something called scatter, which essentially scatters particles across the object. So we can plug the grid here, and we can plug in the grid here as well. And you can see nothing is happening, which might be a little bit confusing at first. But once you get into the nodes, you actually have to specify the target, and that's the toroid. You can select how many points you want. In this particular case, let's just go to 200. You can do that via point total, density, or points per voxel. We're going to leave that as is now and worry about why we actually can't see any difference here. And the reason is because the scatter actually creates a particle system. This particle system can be meshed again, as we've said in the beginning. You can mesh particles, objects, and primitives. So we can see here from particle nodes. Once we hook that up, and then we can output the grid to here, and you can see that's actually how many did we have? 200 particles. So if I actually change this to 20, you can see now there's only 20, but we're going to leave that at 200, and they're essentially going to be generated on the surface of the mesh to volume. We can also do a fill interior, which is actually going to generate them only on the inside. And that's beneficial because what we can easily do if you wanted to do bubbles in a glass or any beer bubbles, any sort of things of that sort of type, makes it very easy to do these. And all we have to do essentially is go to the Boolean operation here, plug our original into the original grid into the input, and the particles here we're going to, with the fill interior mode so that they only generate on the inside, we're going to actually subtract them from our original mesh and plug that into here again. Now you can see that some of them obviously are still on the surface because it's very close to the surface. So in order to get rid of that, we actually want to dilate, or we actually want to erode our original toroid so that the scatter is happening on that part. So to do that, we're actually going to use a filter, plug the filter into grid. In here, let's erode, and let's just do something by 3, for example. Plug that into grid, and under scatter now, we want to not have the toroid anymore, but the actual null object that we were creating. You can see it appears as if they're disappearing, but if we disable the original toroid here and enable VPR, go to the surfaces and make this, you can see that every VDB has their own surface or have their own surface created. If we make this now transparent, you can see that we now have bubbles inside that are essentially cut out. You can of course turn on smoothing and it's going to look a lot better. And so with this, if you now go to the scatter here and wanted to say only 20, you can see that, to your full content, you can essentially, do, whatever you want. It's a nice little way, and you can see you're almost using all the nodes that are essentially required for VDB. It's just to recap, you're making an original, or you're making an initial grid from your toroid. You're shrinking that grid. Then on that shrinking grid, or on that shrunk grid, you add particles. Then you take the particles that are being created, mesh them again, subtract them from the original, and that's essentially all you did here to get this result. So let's take the particle idea a little bit further. Let's take one of the example scenes that I've provided and go here and load the scattered particles. And what we can see here is essentially a sphere that you can see here, there's the sphere object right here that's being meshed on the null right here. And that mesh is emitting particles that are being meshed again. And as you play forward, you can see that those particles are actually falling down, hitting the toroid, and then they're going to hit the ground plane. So essentially kind of like a liquid simulation. And it's very easy to do that. We go to our level set here, go to the properties, and what you'll find now is, again, a very similar thing where we have a mesh to volume here of the cube. We have a toroid right in here. Those are being combined. And let me open this up a little bit more. Those are being combined into a collision that are being piped into a solver. The solver we're going to get into in a second. And we have our third mesh to volume here, which is the sphere. The sphere has particles that are being emitted, as you can see here. And then, again, those particles go into the particle system of the solver. Now, the solver essentially just is a sort of thing that allows you to look at frames prior and within context. So you can see sort of there's a couple different steps you can go into, but these are the defaults of the solver essentially. I don't want to go into it too much. It's much easier later on to do a couple of videos on each thing individually. But essentially, a solver just allows you to take prior positions into account and do something for the next frame. So all you really need to know for this particular thing is that the voxel sizes, they all need to match between the different grids. You have your collisions right here, which is combining the toroid and the plane on the bottom. You're piping that into the collision grid of the solver, and then you have the meshing of the sphere plus the particles that are being generated on top of it, and the output is just plugged into a filter grid, which all the filter is doing a little bit of smoothing and then outputting it here. Again, since the surface gets created, we have just on the volume mesh, we have just some greenish type surface, but you can change that to anything you want. And with that, you have a simulation. Now, with the solver, you can't, if you start scrubbing, you can see that it will actually go not very good. You have to start, it's a frame by frame sort of thing. Once you're done, you can go into the evaluator and you can also bake this entire simulation out. For that, you have a saver. The saver you can just plug to the back of the grid, define an area where you want to save, then you can either save a single frame or you can save an entire sequence. As soon as you click save, it'll run through the timeline and saves them as VDBs. Now again, these are not LightWave objects or anything like that. You would save them in a traditional sense on how you've always done that, but these are VDBs, level sets, that you can then load in as a VDB. To load a VDB in that was saved via the level set or via the saver here, you would just go to the OpenVDB info node. In here, once you open that up, you can select a VDB file, and it usually, if it's a level set, it'll just come with a single channel. You select a channel, which is typically a level set, sometimes density. It really depends where it's coming from, and then you just hook up you hook up the output grid into the input grid here, and that's what would give you the simulation that you'd want. And that's essentially quite a few of the things that we talked about in terms of the VDB tools. One thing that might be kind of neat to see real quick in terms of one of the other things that you can do, if we clear this out, we're going to start with a sphere and a toroid again. Might get boring for you, but trust me, it's actually pretty cool. We're going to position it again. And do you remember from the beginning of the video where we had these sort of just meshed? But there's also other things that we can do, and I'm going to help myself here a little bit and go to my presets, the OD node presets here. And we can add a level set. Let's hide these real quick. Actually, we're only going to hide the toroid, and you'll see in a second why. So we're going to add a null here, and we're going to load, apply a level set here, go to the properties, and apply the bulge preset here. And that sets up a little node flow. So in here, we can essentially say, give me the toroid, and on the other one, you want the sphere. And so what you actually see now, that you can see that there's a little bit of a lip here. So if I'm dragging the sphere, actually, you can see that this lip gets, as I'm sinking the object into it, you can see something pretty cool, in terms of, it takes a second to update, but you can do these really, really cool, transition effects. And it's essentially really, really easy. It's not complex at all. It might seem a lot complexer than it is, but if you look at the node flow here, it's the same nodes as you've seen before. These ones here are just the mesh to volume. They're controlled by a single voxel size. Then you have a dilate, which essentially just makes the object a little bit bigger. It combines the two objects together. It then subtracts the original from those new objects with booleans, and essentially later on puts them all back together, smooths them at the very end, and that's how you get an effect like this. And again, if you wanted to add, for example, let's just say we wanted to add a cube here, and we'll move this over, and you can see that cube does not have that effect. If we wanted to add that effect now, that's very easy. We go to our level set, and we'll pick one of the ones here that, let's see, this was the sphere. So all we have to do here is create a new mesh to volume, pick our cube here, make sure we have world selected so that all the transforms transfer. We're going to hit the voxel size, add it to here, and then we just take a look at and make sure that whatever this is connected to, well, first actually we need to combine them. So we're going to add a CSG here, combine these two, and whichever this original output is connected to, that's where this output from grid goes to. So we're going to put it once here. We're also going to put it here, and the last one is here, so we're going to put it right there. So now if we actually move this to the side and we update our animation here, we can see that nothing happened, and that's probably just because I connected them in the wrong way. And that is because you can see here this is a level set. Of course, this needs to be a level set as well and can't be a fog volume. And once that is done, you can now see that we have the transition effect as we wanted it to be. And it's really pretty cool because, again, it doesn't matter the complexity of the object. It's just something that you can easily add together. And once you have these little snippets, it's essentially always reusing the same tools. It's much less scary than when you actually look at the whole thing and go, oh my God, that's a lot of nodes. It's really not, and it's all fairly logical. And again, you're going to use the same blocks every single time. So one last thing about level sets, I'm going to show one more thing here. So if we wanted to create a snow-covered scene or something where snow has fallen onto specific objects, we have the scene here. There's essentially 3 objects here. And this sort of bounding box type object that you see here was just something that I did in Modeler, where I selected the top facing polys or any poly that where I wanted to have some snow on them. And then if we go to the level set, again, we added a null. In the level set, we essentially have a mesh to volume, which is just our winter layer 2, which is the layer on top here. We're going to grow this out a little bit. So we're dilating it just a little bit. Now I'm using something called the gas solver, which is just a thing that essentially it makes it behave like a gas. However, that only works with fog volumes and not level sets. But there's a node here where we can actually select the, well, actually I'm going to show what each part looks like. So if we look at it here, you can see that that's essentially, you know, what the snow or what my source looks like before we apply it. Then I'm going to convert that into a fog volume, which is just down here, which is, you can convert any level set, which is any of these outputs, into a fog volume, which is what is required by the gas solver. Then into the gas solver, you can see also it requires a collision grid. You can see that here I have the winter layer 1, that is the word itself. And once you have that, I'm going to output that again. So once you have done that, in the gas solver, it's just a default gas solver, except instead of the temperature being at 700 degrees, I'm actually making the temperature go down. Then because the output of this is of course also a level set, because we feed a level set in and it only works because we feed a fog volume in, it will also be a fog volume and we need to convert the fog to a level set again. And then I just smooth the result a little bit. And what we actually get when we hit play, again, this is also a solver, means it's time dependent. So what we actually get when we do this is, you can see now that, you know, every frame, there's a little bit of snow. And I'm going to pause it on the last one here. And so we have something like that, which essentially is, let's just say, that's what I wanted in this particular case, and it looks like, you know, some snow flowed down, you know, the letters. And you can then take that, of course, this null object now, even though initially it's a null, you can see that it has points and polys. You can save that as an object and export that, and you have something that's, oops, don't want to move it, and then you have something that's essentially generated, you know, like some snow generation. And again, it's completely procedural. At any point in time, you could swap out each of the objects, whether it's a house and you just selected the roof section polys and extruded those a little bit, then this would work just as well. And you can use the same sort of setups, you know, every single time. So with that, I'm gonna finish the level sets, and now let's move over to the fog volumes for just a minute. Don't need those anymore. Okay. So now let's look at fog volumes. So we're going to start with our beloved toroid. And we're going to make it not renderable and make it hidden. Again, to add any sort of VDB, whether it's a fog volume or level set, you have to add a null. And now to get to the fog volumes, it's actually going to be under the primitive type. There's OpenVDB, and we're going to open the node editor in here. Looks very similar to the level sets. It's of course the same node editor as we've always been used to. And if we go to the VDB tools, we have the same VDB tools. Now again, we wanted to create a volume or smoky object of our toroid. So we're going to select mesh to volume, and we're going to select the toroid here. This time we want to keep it as a fog volume. Again, we're going to put this into world. And now, without explaining a lot more, we're going to just pipe that into the scattering grid and also in the absorption grid. We don't really see anything in here. You can get a sort of similar, a sort of representation by hitting the I button here or visibility button here. You can see that we'll see something, but the better representation is actually just looking at it in the VPR renderer. Now, the I button here, it does come in handy, but it will also slow down your whole simulation if you're doing one, just because it has to update the frame. So typically when I run simulations or anything with the gas solver or the solver, I turn this off. But it is beneficial to have, at certain times, because sometimes VPR might be a little bit too slow. Now, the interesting bit here is you can see that we just have a sort of toroid, looks a little bit faint. We can easily increase the visibility by just changing the scattering scale here. So let's just change it to something like 20. And you can see that we see something much more defined. You can see a little bit of the pixelation here. And that is essentially, one is the interpolator is point. I recommend quadratic. But then also sometimes it is simply because you have too much of a value, because again, voxels are cubes. So it fills out too much where there actually shouldn't be something. So if we put this to something more like 10, you can see that that's more smooth than what you had before. Now, adding a noise to this is exactly the same way as what we would do with level sets. We're going to do that in here again. Add a noise. We're going to add our procedural tool. Again, you can use any of the procedurals. It doesn't really matter, but I really love the new procedural tool. We will pick turbulence here. I'm going to make it very visible at 100%. Change the white here, and now let's just pipe that value into noise. Hook up the input and put this both into absorption, and you have something pretty quickly here where you can see, like, you can still see the toroid, but then again, it could be any shape. You can easily replace any shape. You wouldn't have to rewire anything. It would always look the same. Now, the one thing to remember when you add a noise to a VDB set, if you rotate this object now, or if you add noise this way, it will never change the shape of the toroid. So it'll never grow the toroid, or it'll never, the noise doesn't really influence the toroid. It just renders it in a noisy sort of way, if that makes any sense. Like, the shape here is never, changed. That doesn't mean that you can't do that. It's just if we apply the noise this way, it's essentially a static noise. Even if you animate the noise in here, it'll just basically move the noise through the toroid, but it won't actually change the outlines or the shape of the toroid. If you wanted to do that, there's something called advection. So if we look into that, I'm going to load one of the example scenes that I provided. So if we go here, you can now see that as I'm moving through, that the noise, it's a little bit hard to see here, so we're going to use this setting here. So you can see as I'm moving through that the noise actually goes outside the boundaries of our initial toroid, and with that changes over time. So if you had an object where you wanted undulating noise, where the noise goes a little bit outside of the boundaries, because you want it to be more organic versus a cutoff sort of thing, then you need to use advection. Might be a big word. Don't let it scare you. It's a very simple thing to use. You essentially make a boundary. You essentially inject velocity into the advection node. So here we start with, again, our toroid level set world. Then we have an advection node, which you can use the defaults. Again, I don't want to go into the different settings now, but just use the defaults. And what it requires a velocity grid, which is essentially something that tells the voxels where they need to go, or how they should move within the grid. It requires a velocity grid. We have, under the OpenVDB tools here, we have the where is it? Right down here, the velocity. velocity requires a reference grid. Now, a reference grid essentially is just a bounding box in terms of like, you know, a grid on top of your grid. So essentially just a cube. You can make it a cube. If you don't make it a cube, I believe it actually you could use the original object. It will just take the bounding box of the original object. But you know, sometimes you might want to define something else. So I tend to create myself a quick bounding box, which is just a cube. And then you pipe in a velocity into that. Velocity could just be bump. You can also, let's say if you wanted to do some sort of wind where you wanted to have the velocity go from left to right, all you would have to do is add a vector constant. 1 second here. So let's say we wanted to just move it in the x, so we just do a vector of 1, which is a direction x, nothing on y, nothing on z. If we pipe that into here and go to the beginning, you should just see that the volume now moves completely to the right. Again, that's just a simple move. You can combine that with other vectors to get you know, more windy, wavery type thing with other noises. Should be, you know, very, very easy. Otherwise, all the other things that we've covered in the level sets still apply here. One cool thing with the fog volume is the gas solver. So I'm going to load another example scene here. So this gas solver here, if we just play it back, is essentially just a cube. And again, we're doing a mesh from cube. We're doing a mesh to volume, to a fog volume. And you can see it's these sort of nice gaseous kind of puffs that you're used to seeing in other softwares that can essentially create VDBs. And you can see there's one here, then it stops for a little bit, and then there's another one coming. Different things like that. And the way to set that up, if we just let it go a little bit longer, is when we just look at one frame here, just so that you kind of get an idea of what it looks like. It's a really, really cool effect, and of course it's totally driven by the motion of the box. So if you're moving the box around, you know, obviously you'd have the correct motion of all these kind of things. Again, it's a very easy thing to set up. We'll go to our smoke VDB. You can see I only have an object and a smoke VDB. We go to the node editor, and in here all we see is essentially a mesh to volume. That mesh to volume just has the cube object. We say it's a fog volume. I decrease the size of the voxels a little bit just to make it look nicer and less defined. Then I'm adding a little bit of a noise, and the reason why you want to do that, because a gas solver, again, these are just the defaults of the gas solver. If you think about, you know, lighting something on fire, or smoking something, if the entire surface was always evenly, you know, if every part of a surface was getting the exact same values, you wouldn't have a lot of undulation, or, you know, some parts that smoke more, some parts that smoke less. So you want to just add a very simple, you know, noise grid here. I just used, again, a procedural node, very easy default values pretty much, piped into the noise, and then you feed that into the source grid of the solver. In the source grid of the solver, you typically give it a temperature. By default, it's 700 degrees. And if you were to use it like that, it would just give you one puff and then do a continuous stream. So in here, we just simply, I use 700 degrees to a certain point in time, then set it to 0, which doesn't mean that it's going to stop emitting. It just means that the temperature itself, which is going to drive the gas upwards, is less. And then I'm going to increase it again, and that's how you get the puffs. That's the only difference from the default. And then you just pipe that again into scattering or absorption, you know, or both. You can pipe in the temperature grid to the emission grid to get some of the colors in terms of, you know, if you want hot and cold. And that's essentially the gas solver. It's very easy, you know, you can very quickly just replace this with another object. And you know, now you have something else that's on smoke, or that's on fire. And I think, or I hope, that that is enough to get you guys started. I wish you good luck. It's really a lot of fun, kind of addictive. Don't let the nodes scare you. It's very, very, very cool.